The title of this presentation is Intersection Angle Between Shear Fractures in Sea Ice. The main message of the talk is that current sea ice model used in the community overestimates the intersection angle between shear fractures in the pack ice. Now, in the context of the standard viscous plastic model, this is expected from theory and also from simulation that matches the theory. Now, when we fix the yield curve to the Mohr-Coulomb yield curve, which is typical for granular material, and we use an internal angle of friction, which is derived directly from observation, we still overestimate the intersection angle between shear fractures. This is something that needs to be looked at further. Now, what we will see in this talk is that what happened post-fracture has a large influence on the intersection angle that is simulated by sea ice model. Now, I would like to acknowledge the work of Damien Ringeisen and Mathieu Plante, two former PhD that are now postdocs and that led to papers on this topic, and other co-authors, Niels Schotter, Jean-François Lemieux, and Martin Losch. These are images of the fracture pattern in typical granular material. We see ice on top left, sand, concrete, and clay. What we observe is that the fracture lines are not oriented randomly, but they have a very specific direction which align themselves with respect to the large-scale forcing. Now, if we want to know how they align themselves, we can do a very simple experiment in uniaxial loading of a concrete pillar, for example. And what we see is that the fracture line align themselves at some angle from the main loading axis in the material. What happened along the fracture line is basically shearing deformation with some convergence or divergence. If we look at this spatially, what we see on the right are observation from our GPS for 2 different days. And on the left are simulation from 2 models, 2 sea ice models. On the top left is the NextSim based on the Maxwell elasto-brittle model. And on the bottom left is the MIT GCM with the standard viscous plastic rheology at 2 kilometer resolution. So what we see from this figure is that the density of kinematic feature or fracture line is good and well reproduced by the model, but that the angle of intersection between those fracture line are not in line with observation and are larger than what observation shows. This is the same results, but presented as a PDF as a function of the intersection angle. In orange, what we see is the observation from our GPS. And we can see there's a peak in the distribution between 30 and 60. And the model, on the other hand, shows that the large number of deformations simulated by this model have large intersection angle. And this is the case for the standard viscous plastic model, the elastic viscous plastic model, the Maxwell elasto-brittle, and the elastic anisotropic plastic model. In the case of the MEB, there is a peak in the distribution, but it's around 70 degrees, and it's much larger than what is being observed. So what we're going to do is a simple uniaxial loading test of a sea ice sample and test different rheology and different flow rules and see how they compare with theory. So there's basically 2 theories of fracture in the community that is being used for granular material. The first theory is the Mohr-Coulomb, which basically says that the yield curve is that of static friction. That is friction between 2 solid surfaces. And tau, the maximum shear stress that can be resisted, is linearly related to the normal stress between 2 surfaces. What the fracture angle that result from such rheology is shown here, like with the dashed yellow line, and is somewhat lower than 45 degrees. Now, you can predict the fracture angle from this simple theory, like geometrically, and this angle theta is equal to pi over 4 minus phi over 2, where phi is the internal angle of friction. So for instance, if you have an internal angle of friction of 45 degrees, typically used in the community, well, then you're going to have a theta C of 22.5 degrees, or a full angle between the two yellow lines here, which is going to be again 45 degrees. So this is the reason, which is in line with the observation, and this is the reason for the choice of 45 degrees for the internal angle of friction used in models. Now the second, so this theory is entirely based on the external loading and the internal stresses within the sea ice. And basically what this theory says is that the ice will fracture on a plane where the shear stress, which is trying to fracture the material in shear, to the normal stress, which is trying to keep the material together, where this ratio is maximum, this is where the material will fail. Now you can imagine that the granules or the grains or the floes on the micro scale might be aligned in such a way that it will favor a plane of fracture that is different than that is specified by the Mohr-Coulomb criteria. For example, it could be favoring a fracture along a plane where the stresses are lower than these maximum values simply from the orientation of the grains. So I'll show a simple example on the next slide. This is a simple model of a granular material represented by a cylindrical disc. What we see here is on the large scale a shearing motion, T, with a normal force end. The red dot here indicates the contact normal between flows along the plane of fracture. Okay, and basically the dashed dotted line here is tangential to those red dots between adjacent flow where the contact normals are located. So basically, if you shear the material on the large scale, on the small microscopic scale, the flow will have to slide along these dashed lines. If you look post-fracture here, basically those red dots are still opposing the motion. And basically the force on the microscopic plane are opposing the large scale motion. What you see here is open water. And typically when we think of open water, we think of a weaker sea ice. But in the case of a granular medium in slow continuous deformation, where the flow are always in contact with one another, when you have open water, it means you have contact normal that are opposing the flow. And basically it means that you have a high shear resistance. When the contact normal are helping the flow, as on the right panel here, basically the open water is closing, you have convergence, and then you have a weak shear resistance of the material. So the angle that this dashed line is doing with the horizontal is called delta, and delta is called the dilatation. It's a measure basically of the divergence along a shear line. So what you have in this type of material, when you have high divergence, you have high shear resistance, and when you have convergence, you have low shear resistance. And the corresponding yield curve are like this. Basically on the left, you would have a yield curve with a typical internal angle of friction. When you have large divergence, you would have the internal angle of friction, which is higher. And when the contact normal helps the flow, you would have an internal angle of friction, which is small. So basically, you have a material here with an internal angle of friction that varies spatially and also varies in time. And it's also a measure of the history of the deformation in the pack ice. The second theory basically is based on this dilatation that we've just seen. It's expressed in the exact same manner as for the Coulomb theory, but the angle of fracture, theta c, is equal to pi over 4 minus now delta over 2 instead of phi over 2, delta being the angle of dilatation. In this case, this is not the yield curve, but rather the plastic potential, because it's the plastic potential that determines the post-fracture flow of the sea ice. So now we're back to our uniaxial loading experiment. We're going to be testing like different rheology and different flow rule, normal or non-normal. So if we start with the simple standard viscous plastic rheology of Hibbeler with a normal flow rule, it's expressed here in stress invariant space, so that this is the mean normal stress, and this is the maximum shear stress. If you have a stress state on the red dot here in the ellipse, basically in this type of, when you have a normal flow rule, the principal axes of strain rate and stress coincide. So basically what you have here is epsilon1, the mean strain rate, which is the divergence, and epsilon2, which is the maximum strain rate. And the normal to the yield curve gives you the relative importance of how much divergence there will be compared to shear strain rate on the plane of fracture. So when you test a rheology like this, in uniaxial loading, what you see is like failure patterns that are very similar to what you observe in the field. When you plot the intersection angle as a function of the ellipse aspect ratio, which is a measure of the shear strength of the material, you have the simulation here as the red cross, and the Mohr-Coulomb theory as the dash black line. So you can see that the theory matched very well with the simulation result. And the simulation result for all elliptical yield curve aspect ratio basically are too large compared to observation. For the standard value of 2, it doesn't look too bad, but we need to remind ourselves that if we had confining pressure in this type of rheology, the intersection angle would increase and it would go further away from the observation. And again, this is against like observation, like granular material. The intersection angle between fault line in granular material is independent of the confining pressure, unlike that for the VP rheology with the elliptical yield curve. Now, if we dissociate the yield curve from the plastic potential, what we do here for simplicity is that we use an elliptical plastic potential in red with the standard elliptical yield curve in blue. You can see now that it's a non-normal flow rule because the flow rule is perpendicular to the plastic potential, and it's no longer perpendicular to the yield curve because they have different aspect ratio. So when we test this, what we see again is a failure line that are very similar to what is observed in the field. And if you have a plastic potential with a small elliptical aspect ratio, that is like a fat plastic potential, you see fault lines that are much more acute, like the angle is much more acute and more in line with the observation. When you use a very thin plastic potential, the angle are larger and further away from observation. When we look at it in terms of fracture angle as a function of the plastic potential ellipse ratio for various yield curve ellipse ratios. So we're going to focus on the red now because the red is the ellipse ratio for the yield curve of 2, which is a standard value. So we see here that if you have a plastic potential ellipse ratio between 1 and 1.5, the fracture angle will be in line with observation. So we might be tempted to say, okay, well, this is it. We can simply use this kind of plastic potential. But we have to remind ourselves again that if we had confining pressure, this red curve would move up and would move away from the range of observed value. And another thing is that the deformation along the fracture line in such a rheology will be completely defined by the ellipse aspect ratio of the plastic potential and the yield curve. And we know that this is not the case in reality. In reality, you can have divergence or convergence along a fracture line, and this can vary in time. This is not the case for an elliptical model like this one. So basically, this is not the answer to the question. Now, if we look at non-convex yield curve, in this case, like we look again at the Mohr-Coulomb yield curve, we're testing this one now with no dilatation, which basically means a pure shear deformation without divergence along the plane of fracture. So in order to achieve this in the context of an elliptical plastic potential, we use one that has a very high elliptical aspect ratio. in such a way that the normal to the curve is always pointing vertically upward. This means that the flow rule is pointing upward and does not project on the x-axis, which is how much divergence there is in the flow field post-fracture. So when we test such a rheology, we get the simulation result here in blue. This is the fracture angle again, and this is the slope parameter. This is the internal angle of friction, basically. So what we see is that the simulated internal angle is larger than the range of observation and does not match the Coulomb angle theory. Okay, and it does not match either the Roscoe angle theory, which is based on dilatation. It basically lies somewhere in between, and the dashed dotted line here is called the Arthur theory. It's basically the mean between Roscoe and Coulomb. So basically we have now like a post-fracture, that we have like a fracture angle that cannot be explained by either theory. We will see later that how we simulate things post-fracture has a large influence here on this fracture angle. If we look at it now in the context of the Maxwell elastobrittle rheology, we have again the Mohr-Coulomb yield criteria. When we have a stress overshoot, which is written here in red as sigma prime, we return the stress back onto the yield curve. If we use the dashed black line that goes through the origin, this is the standard approach in the MEB model. If we go at any other angle, this is a generalized return path that was published by and worked by Mathieu Plante here and was published recently. So if we look at this non-Maxwell elastobrittle rheology, and we do uniaxial loading test, what we see again is a fracture angle that are similar to what we observed in the field. And when we plot this intersection angle, theta, as a function of the internal angle of friction, phi, we see that all the values, again, lies above the observational value shown in green, okay? And that they, again, do not match Coulomb angle from the theory of the Coulomb angle, nor the Roscoe angle. Again, it's somewhere in between, which is a mixture between Roscoe and Coulomb. We can also see like the different colors here. These are different angle, different return path, like to the yield curve that I was showing on the previous slide. And we can see that what we do post-fracture, in this case, how do we return the stress from a state which is an overshoot back onto the yield curve, has a large influence on the internal angle. So basically, what we're saying is that we need to be careful about what we do with the flow rule or post-fracture. In conclusion, fracture angles with convex yield curve, with or without a normal flow rule, match Mohr-Coulomb or Roscoe theories. This is the icon here to remind you of the result that we presented earlier. The fracture angles with a non-convex yield curve together with a plastic potential in the context of the VP rheology, an evolution equation for the dilatation or stress correction scheme in the context of the MEB, do not match Roscoe theory and instead are affected by both dilatation and internal angle of friction. So basically, it is a blend between Mohr-Coulomb and Roscoe theories. And this is something that we do not yet fully understand why, and that we need to investigate further. So thank you very much for listening.